So thanks everybody for coming back for the second lecture in the Introduction to Oceanography. Today we're mostly going to, today we're going to tie up some loose ends about units and scientific notation. I'll try to get through that relatively quickly. I know it's not the most exciting thing in the world with respect to oceanography. And then hopefully we'll get a chance to start talking a little bit about where the oceans came from. And this will set up the next few weeks where we start talking about physical properties of the oceans and the basins in which the oceans currently occur. And actually, this is a picture that gets ahead of us a little bit, but it's worth explaining a little bit. Has anybody here ever been to Hawaii Volcanoes National Park? All right. So Hawaii is one of the US states. It's actually the state where our president was born. And it is a volcanic island chain. And we'll talk a little bit more about why there's a chain there and what its significance is. But it's a big volcano, or a series of big volcanoes. And right in the middle of the national park, which is built largely on the volcano of Kilauea, the most active of the Hawaiian volcanoes, there is a crater. And until last year or something like that, there's a little parking lot over here. And you could just walk on a little path right up to the edge of this crater called Halima'uma'u. And look down in, and there was not much going on. There was maybe a little bit of steam coming up or something like that. The real action at Kilauea was actually taking place farther down slope. That's where the lava was coming out. So that's where you would go if you really wanted to see the exciting stuff. However, not too long ago, a hole opened up right in the side of the crater, and gases started belching out. Very hot. So I'll show you a picture in a second. This is the same thing at night. Okay, and this is the same little hole in the side of the crater, and you can see it's glowing red, okay, so it's pretty hot. And the stuff that's coming out includes, among other things, water vapor, also sulfur dioxide, carbon dioxide, a whole stew of gases. And this turns out to be a modern example of something like the way we think that the water that makes up our oceans got up to the surface of the Earth by D. Okay, so we're going to finish up a little bit our discussion of units. And in particular, we're going to talk about this idea that whenever you report a quantity, which is really the heart of science in some ways, measuring things quantitatively, you need to associate that quantity with a unit, otherwise it generally doesn't make any sense. And there are certain rules for dealing with units when you're doing math on some kind of measurement. And so just to give you a sense of how this works, and this will come up again in your labs particularly, but there'll be a question or two on exams. And in general, when I talk about things, they'll make a lot more sense if you understand what the units are doing when I talk about them. Okay. So in general, if I'm adding or subtracting two quantities, that sum or difference is only going to make sense if the two quantities have the same units. Okay, so if I add some distance in meters to another distance in meters, I'm going to have a result, a total distance in meters. Okay, if I add a distance in meters to a mass in kilograms, that's not going to make any sense at all. What's a length plus a mass, right? And so we need to make sure when we add and subtract quantities that we're adding and subtracting quantities that have the same units attached to them. And in some cases, let's say we had one distance measured in meters and another distance measured in kilometers, we're going to have to do some converting to make sure that they're in the same units before we do that addition. When we multiply or divide numbers that are associated with units, in fact, what we do is combine the units together and make a compound unit. So here are some examples. This is a picture, this is a cutaway cartoon of the Earth. So you can see South America right here. Here's the Earth's crust, the mantle, and the core. We'll talk about these in a little bit more detail later in this lecture, but just to give you a sense of the overall structure of the Earth. So let's just do a simple addition problem with units. So it turns out that the Earth's core, this metal stuff in the center of the Earth, is roughly 3,500 kilometers thick. It's a little more than half the radius of the Earth. And then on top of it, there's a rocky layer, which is actually not purple. This is just for show, which is a little bit less thick, about 2,900 kilometers. Okay, so let's say we want to know the total thickness of both the crust and mantle of the Earth. We want to add these two distances together. We need to make sure first that they're in the same units. And it turns out in this case, we're all set, right? They're both in kilometers. So no worries, we can add 3,500, 2,900, and the total thickness is about 6,400 kilometers. Which turns out to be almost exactly the radius of the Earth, because all the other stuff, in particular the crust and the oceans, are much, much thinner. less than 100 kilometers. Okay, here's a more difficult example that we'll come back to when we start talking particularly about biology in the oceans, because this turns out to be really important for plants or organisms that do photosynthesis in the ocean. On average, as we learned in the last lecture, the ocean is roughly 3.8 kilometers deep. Okay, that's the average depth of it. It's deeper in some places, shallower in others. However, we'll find out that sunlight doesn't actually penetrate very far into ocean water, only about 200 meters. Varies from place to place, but that's a good ballpark number. And so what we want to know is, okay, how much of the ocean is dark? Okay, how much of the ocean is going to be water that has so little sunlight that organisms can't do photosynthesis in it, which means it's going to be kind of funny to set up the base for a food chain. It's an important number to know. So how much of the ocean is dark? Well, in this case, we have two distances, but they're not in the same units. We have 3.8 kilometers and 200 meters, so we need to convert one of them. Actually, it doesn't matter which one, but just for the sake of an example, remember that 1 kilometer is 1,000 meters, so 3.8 kilometers is 3,800 meters. 3,800 minus 200 is 3,600 meters. That's the average dark depth of the ocean. Could also report this as 3.6 kilometers, either way. Okay, so an example for multiplying and dividing units. Here the units actually combine together and make a compound unit. And one simple example that we'll get to when we start talking about the chemistry of seawater is salt. Okay, the oceans are full of salt water, and that salt is made up of a bunch of different chemicals, but mostly sodium and chloride, the stuff that you would have on your table as salt. And so what we're interested in is, okay, what's the salinity of the ocean? If we have, on average, for every liter of seawater, 35 grams of dissolved salt, which is a pretty typical number. If you were to go out to Santa Monica and pick up a bucket of seawater and put it on your stove and evaporate away all the water, that's about what you would have left. What is the salinity? Well, we have 35 grams per 1 liter. Okay, so 35 divided by 1, the numbers are actually pretty easy there, 35. And the units on that salinity are grams divided by liters. We combine the units together because we're dividing them. So we have grams per liter for a salinity. Okay, so we've divided two quantities and ended up with a unit that's combined from the units of the two quantities we divided. Here's another example for a tsunami, which we'll learn are really, really dangerous, in part because they're so fast. And so a large tsunami might cross 1,000 kilometers of ocean, which is something like 600 miles. Twice the distance from here to San Francisco, in something like 1.5 hours. Okay, so how fast is that? Does anybody want to take a shot? We have a distance, we have a time, we're looking for a rate, which is distance divided by time. So what are the units going to end up being? We're dividing kilometers by hours. So kilometers per hour. Okay, and what's the number? What's 1,000 divided by 1.5? Yes, exactly, 666.66 repeating, or we can round it to 667 kilometers per hour. Okay? So I'm kind of over belaboring this point, but I just want to make it clear to you that whenever you write down a number, particularly in the context of science, but actually this is true for anything you bother to measure, always make sure that there are units associated with that number, otherwise the number won't make very much sense. And when you manipulate units, make sure that you're manipulating the units properly. Okay. Particularly for oceanography, we're very often going to be dealing with numbers that are very large or very small. Okay, large like the mass of the oceans, which is like 10 to the 21st kilograms. That's a big number. Okay? And what I just said when I said 10 to the 21st was actually an example of scientific notation, an easier way of describing very large or very small numbers. If I were going to say 10 to the 21st in the normal way we talk about numbers, that would be something like 1 billion trillion kilograms, which is kind of an odd number to work with. So scientific notation is really a matter of convenience, but it's an important part of discussing science. And it's based on powers of 10. So hopefully this is review for most of you, but if it isn't, here we go. So we can put exponents on 10. 10 to the first power is 10 times itself one time, which is 10. 10 to the second power is 10 times itself twice, so 10 times 10 is 100. 10 to the third is 1,000. 10 to the fourth is 10,000, and so on. And what you can see, particularly by the time we get down to the bottom of this, is here we have this thing that's got 5 numbers and a comma in it. Here we have this thing that has 3 numbers in it. Okay? It's getting more compact when you're dealing with a very large number. It goes the opposite direction, too. So any number to the 0 power by definition except 0 is equal to 1. 10 to the minus 1 is 1 divided by 10 to the first power is 1/10. 10 to the minus 2 is 1/100th. 10 to the minus 3 is 1/1000th. 10 to the minus 4 is 1/10,000th. Again, 5 numbers and a decimal point versus 3 numbers. So scientific notation becomes really helpful when you're dealing with very large or very small numbers. And oceanography is an example. Many other sciences also have to deal with very large or very small numbers. There's a little applet you can go to online. That web page is also in the class notes, so you don't have to write it down right now. That will give you some examples of very large and very small powers of 10 in distance, okay, from the size of galaxies to the size of atoms or nuclei of atoms. So not only is scientific notation really helpful from the point of view of talking about really big or really small numbers without having to write out lots of digits, it's also helpful for doing math, okay, because it allows you to split up a number into the part that has to do with how big or how small it is, and then the accurate numbers that tell you in detail what number you're talking about. And so as an example, talked about this on Friday, how many seconds are there in a year? Well, 365 days, roughly, by 24 hours per day, by 60 minutes per hour, by 60 seconds per minute, ends up with something like 31 million seconds per year, which is a number that all earth science students eventually have to learn because we go back and forth between seconds and years a lot. Okay, this is a pretty big number, 8 digits and 2 commas. We can also convert it to a number between 1 and 10, and a number that's some power of 10. Okay, so 31 million is about 3 times 10 million. And this number we can turn into 10 to the power. What power is that going to be? 7. Right. So the number of seconds in a year is 31,536,000, or about 3.15 times 10 to the 7th. Okay, and this is basically scientific notation. Whatever number you're working with, you can transform it into a number between 1 and 10, which is called the coefficient, times the power of 10, which is the exponent. And in fact, once we do this, manipulating scientific notation becomes a lot like manipulating units when you're doing math. So if you add or subtract numbers that are in scientific notation, in order for that addition or subtraction to make sense, you need to make sure that you're dealing with numbers that have the same exponent. Okay, so if we want to add 3.5 million, 3.5 times 10 to the 6th, to 150,000, 1.5 times 10 to the 5, we need to convert one of them to 10 to the 6th or to 10 to the 5, so they're both having the same exponent. In this case, we can turn 150,000 into 0.15 times 10 to the 6th. And then once that's done, you just add the coefficients. 3.5 plus 0.15 is 3.65, and the exponent stays the same through the addition. The same goes for subtraction. Okay. When you subtract numbers, you also need to make sure or convert them so that they both have the same exponent, and then you just subtract the one coefficient from the other coefficient and keep the exponent the same. Multiplication is really where this comes into its own as a convenience for dealing with large and small numbers. When you multiply two numbers that are in scientific notation, you multiply the coefficients and you just add the exponents. So here we have 3.5 million times 150,000. That would be a real pain to write out long multiplication style. You'd have to have like 7 rows. But you can just, in scientific notation, multiply 3.5 by 1.5 and take it to times 10 to the 6 plus 5 power, 10 to the 11th power, right? And with division, you subtract the exponents and divide the coefficients. Okay, so it's exactly the same idea, you're just subtracting instead of adding. Okay, and if, in some cases, it's more convenient actually to go back to non-scientific notation. All right, let's start talking about the cool stuff, or the cooler stuff I'll let you form your own opinion. So today we're going to sort of talk about, we're going to start talking about oceanography, but we're going to try to place it in context. And in particular, we're going to talk about oceanography as a planetary science. We're going to talk about oceanography as potentially an astronomical science. And then eventually we're going to talk about it as an earth science by the end of the day. Okay? And so we're going to go through sort of these three levels in which you can view oceanography, depending on the scope of your interests. Okay, so we're going to talk about the Earth's position in space and oceans potentially on other bodies. We're going to talk about the gross structure of the Earth, the crust, the mantle, and the core, and you're going to be able to see some examples of the Earth's crust and mantle and an example of a core from another planet. Unfortunately, we don't have cores of our own planet. Actually, that's probably a good thing, but nonetheless, you'll see a core from another planet. We're going to talk a little bit about where Earth's water came from. And then coming into the next week or so, we're going to start talking about where that water sits on the Earth and why it sits there. So the shapes of the ocean basins and major features of the ocean basins. This, by the way, is a picture of Titan, which is the largest moon in the solar system, I think. It's a moon of Saturn. And you can see it has this nice blue atmosphere around it, which is actually about the same pressure as the Earth's atmosphere. And actually not that different in composition. It's nitrogen dominated like our own atmosphere. So here's our solar system. This, by the way, is not a picture to scale. It's crammed together so you can see all the dots. Actually, the planets are very far apart. And if I tried to show them to scale on this screen, you wouldn't be able to see most of the planets. They would be smaller than a pixel. However, we have the sun in the center of our solar system. We have the four inner planets, Mercury, Venus, Earth, our moon, of course, Mars. And then we have the outer planets, Jupiter, Saturn, Uranus, and Neptune. We have other bodies, okay, which have a variety of names, dwarf planets, minor planets, meteoroids, comets, depending on what they're made out of, where they lie in the solar system, and how large they are. Perhaps the most famous of these is Pluto out here, which in this picture is actually depicted as a planet, but it got demoted a few years ago. It's no longer considered a real planet. It's a Kuiper Belt object. And there are, of course, comets, and there are asteroids, particularly between the orbits of Jupiter and Mars, but there are also asteroids that cross close to Earth. We try to detect those and find out if they're going to hit us. It's not clear if we could do anything about it yet, but it's something we think about. Okay, so this is oceanography. It's not planetology. Why do we care? And the answer is that actually, in the past decade, and especially, we've become interested in the possibility that oceanography may not be just an earth science, that there may be oceans to study on other worlds in our solar system and out of our solar system. Okay? And it turns out that there are some pretty good candidates. We're probably not alone in having an ocean. Okay? We are obviously most confident in the presence of an ocean on the Earth, but we have pretty good evidence for oceans on other ones. So in particular, Europa, which is a moon of Jupiter, okay, has a briny ocean, probably at depth below an icy crust. We'll see a picture of that in a minute. Titan, the one I just showed you a picture of, the largest moon of Saturn anyway, has maybe not as big as an ocean, but it has bodies of water on its surface, bodies of liquid on its surface. They aren't actually water, they're probably liquid methane. And in the past, not at the present, there is some evidence that there were large bodies of water on Mars, in particular near the North Pole of what is now the North Pole of Mars. And of course, for sure we know that there are oceans on Earth. Hop on the Santa Monica #1 at the bus stop, spend a half hour and prove it to yourself, if you'd like. Okay, so let's go through these in a little bit more detail. The planetary science of oceanography. The classic example of this is Europa. This is a picture of Europa taken by the Galileo spacecraft, which orbited Jupiter and took very high resolution pictures of many features of that system. And you can see right away, first of all, that it's kind of a bright whitish color, right, with these reddish streaks and stuff on it. Okay, this is an icy surface, mostly water ice. There are various pieces of evidence to indicate that that's true, but hopefully just looking at it, it's not too surprising to you. Okay. And there's a funny thing about this moon, which is that there are almost no craters on it. Compare that to our own moon. You look up in the sky at night, you see lots of craters, right? And if you see pictures of the moon from the Apollo program, it's basically covered in craters. And that's actually pretty much a ubiquitous feature of any body in our solar system that's not active. If the surface isn't being created and destroyed on fairly rapid geological timescales, hundreds of millions of years, which is actually fast for Earth science, then it ends up being coated by craters because everything flying around our solar system just gets pelted with debris from time to time, okay, and accumulates craters. Here we have a body that has very few craters on its surface. Here's one really prominent one. Here's maybe another one, okay, but not very many. Okay, so this suggests that there's something going on this moon. It's resurfacing itself on a fairly rapid time scale, at least on the order of the age of the solar system, which is something like 4.5 billion years. This has resurfaced itself at least once and probably many times. Okay, and there's actually geophysical evidence to indicate that what's under this stuff is liquid water, salty liquid water, in part because it has a certain magnetic response to Jupiter's magnetic field. Jupiter has a really strong magnetic field, and as Europa moves through that magnetic field, it's acting as though there's some layer inside of it that's conductive, okay, and salt water conducts electricity, and therefore that's one piece of indirect information, particularly the way it responds to Jupiter's magnetic field, that there is a layer of salty water at depth in Europa. Yes?
What does it mean when you say resurfacing?
Okay, so you can see this and see that it's not just covered with craters, right? And that tells you that this isn't the surface that's been there for 4.6 billion years, because it would have just been covered by craters since then, if it had been the same surface the whole time. So what was the surface then has been somehow destroyed or written over since then. And in fact, over and over again probably, because there are almost no craters at all, and they keep accumulating in the solar system at some rate. Okay. Likewise on the Earth, you don't see very many craters, you see a few meteorite craters, and that's pretty good evidence that the Earth is resurfacing itself, which we'll get into in gory detail later in the class. Does that make sense? Okay. And it turns out that particularly with Galileo, we were able to get really close-up pictures of some of these areas and actually see the crust getting pulled apart and some of these sort of scratchy features across the surface getting broken up into blocks and replaced by chaotic stuff, new crust on the surface of Europa. Titan is a moon of Saturn, and it probably doesn't have an ocean like we would think of it, but it does have liquid water at the surface, which is pretty, liquid at its surface, in this case liquid methane. The temperature on Titan, that far out from the sun in our solar system, is pretty cold. It's so cold that water would actually be ice. It would be unlikely to melt at the surface. However, there are these features that are particularly obvious in radar pictures. Here, this has been processed, by the way, to emphasize these flat-lying features that have radar characteristics consistent with liquid hydrocarbon. So liquid methane, natural gas, the stuff if you turn on your stove and you have a gas stove that comes out into the room and smells funny. Actually, it's not the gas that smells funny, it's stuff that the gas company adds so you don't blow up your house. Nonetheless, these natural gas lakes, particularly near the poles, once you get away from the equator of Titan, there seems to be liquid at the surface. You could call this maybe a small ocean or a sea, but it's a sea of hydrocarbons, not a sea of water. Oh, yes, arrows. Okay. And then finally, Mars. And there is no ocean at the surface of Mars. Okay, we have pretty good pictures of the surface, no evidence of liquid water there. It's too cold, and the pressure in the atmosphere is too low. However, if you look at an altitude or elevation map of Mars' surface, which is what the colors here indicate, so red colors and white colors are high areas on the surface, and the bluish and purplish colors are low areas on the surface. What you can see here is that Mars is kind of split into two parts. Okay, there's the southern part, which has lots of features that look like craters and is generally high in elevation. And then there's the northern part, which has some craters in it, but is generally much flatter. Okay? And one idea is that this flat northern part of the planet used to be an area where water accumulated at the surface and has since disappeared, either frozen into ice somewhere, turned into water-bearing minerals. So this might be an example of an ancient ocean that's now gone. Okay? And by the way, this feature up here is the modern ice cap on Mars. And we've sent a couple of spacecraft to the Martian surface, actually several spacecraft, Gusev Crater rover Spirit and Meridian and Planum rover Opportunity. In particular, the Opportunity rover has found pretty good evidence of minerals at the surface that contain water in their structure that may have been originally deposited by water reacting with rock. So there might have been water at the surface that reacted with rock, and that water sort of got frozen into a crystal lattice somehow. Okay. In addition, we have the Phoenix lander on the surface of Mars, which actually appears to have discovered water ice just below the surface of the soil. So we have pretty good evidence that there is ice at the surface of or near the surface of Mars today, water ice, and this various levels of argument that the topographic flatness and lowness of the northern part of Mars may have provided a place for water to collect at the surface of Mars sometime in its distant past. Okay. And then finally, I talk for just a minute about the possibility that oceanography isn't just a planetary science in the sense of something you study in our solar system or on our planet, but there may actually be oceans around other planets, around other stars. And we've gotten quite good, well, not me personally, but scientists as a group have gotten quite good at finding planets around other stars. To date, this is as of last Thursday, 374 planets discovered around other stars. Extrasolar planets, sometimes they're called exoplanets for short. And on one or two, there seems to be some evidence from the way they absorb sunlight from the star that they're orbiting that they may actually have water vapor, at least in their atmospheres. And here's one example in 2007, HD 189733b. This part, by the way, is the name of the star, and then B indicates that it's, I guess, the second planet around that star. And also, interestingly, we've only in the last couple of years gotten to the point where we can actually directly take pictures of planets. And this is one of the first examples of pictures of planets around other stars. This image has been processed, okay? And the big problem in seeing a picture of a planet around another star is getting rid of all the light from the star itself. The star is much brighter than any planet that's orbiting around it. Because the star is actually giving off light, the planets are just reflecting light from that star. Okay? And so that's why this kind of funny speckly pattern, this is removing the light from the central star. This is where the central star would be. But as much of the light as possible has been removed from it. And when that's done, you can see that there are these little specks that stick out. And those are thought to be 3 planets orbiting around this star. Okay? Now, we haven't been able to really combine these things together yet. Evidence from spectroscopy of water vapor around planets in the atmospheres of planets around other stars, and actually seeing an ocean on another planet, right? That would kind of be the greatest thing of all to be able to see, but that's going to take a while to be able to pull off. But we can see planets, and we can observe indirectly evidence of water vapor on those planets, but a liquid ocean haven't quite done yet. Okay, so for the purposes of this class, except for that little diversion, we're going to treat oceanography as an earth science. Okay? We're going to be mostly interested in the oceans of the Earth, which are the ones we know for sure are there. They're the ones we can get at most easily, and they're the most interesting, in part because they have things living in them, including us living right by their shores. Okay, so as an earth science, we're interested in where do the oceans come from? And we're interested in this in 2 ways. We're interested in where the water in the oceans come from, and why are the oceans the shape they are? Okay, why are we on dry land here? Why is there an ocean just offshore? Why is the average ocean depth something like 4 kilometers? And so we'll address those in turn. We'll actually spend much more time on the issue of why are the oceans the shape they are. How do they get that shape? That turns out to be a good lead-in to the concept of plate tectonics, which is critical to understanding oceanography. But we'll spend a few minutes talking about where the water came from in a planetary sense first. Okay? And we have some evidence of where the water came from, but this isn't a closed question scientifically. There's discussion about how much water comes from some places versus others. But we have pretty good evidence that at least some of the water in the Earth's oceans came originally from the bodies that came together to form the Earth in the first place. Okay, so we had, when the solar system was very young, we had a new star forming in the center, which eventually became our sun. And we had materials condensing in a disk around that star in a solar nebula. And the objects in that nebula condensed, and eventually they accumulated into larger and larger bodies, which eventually became planets. Okay? And it turns out that we have samples of what that material was like that collected to form the Earth and the other planets. Okay? And from time to time, these fall on our planet, leftovers from that process, in the form of meteorites. And this is an example. This is the meteorite Monahans. We name meteorites, by the way, after where they're discovered or where they fall. So Monahans is a little town in Texas. I think it's close to Odessa. And this was an observed fall, so somebody actually watched the meteorite fall through the sky, and then they collected pieces shortly afterwards. I think this was in the late 90s. And so here's a police officer holding a chunk of it. Okay, apparently a piece fell pretty close to where some kids were playing. Nobody actually got hit, which is a good thing. And it turns out that in particular this one, if you look very carefully at some parts of it under a microscope, you can see salt crystals, which characteristically have these kind of right-angle cubic shapes to them. And if you look in detail at some of these salt crystals, you can see some actually a little bit. So like here, maybe in here. There are little fluid inclusions in those salt crystals. Okay, so in the salt crystal, there's a little trapped droplet of water. And this is a magnification of a trapped droplet of water from a meteorite, from a salt crystal or a meteorite. And there's actually a little droplet of vapor inside that bubble too. Okay, so here we have an example of a meteorite. Okay, the stuff that originally formed the Earth, accumulated to form the Earth. And in that meteorite, we have salt, which is, of course, the oceans are salty. And in general, we think particularly large grains of salt is forming by evaporation of salty water. And in that salt, we see evidence of water. Okay, so right away we can say, okay, the Earth forms from things that are like meteorites accumulating together to make a planet. We see evidence that those meteorites have water in them, so maybe that's where a lot of our water came from. Okay. In addition, actually, we see lots of other evidence of water in meteorites in the minerals that make up the meteorites themselves. So this is a picture of a section, so a polished slice through the Murchison meteorite, which is a fairly famous one. And you can see it has this kind of yellowish-greenish color, which in this picture indicates the presence of a mineral called serpentinite, which has magnesium in it, it has silicon in it, has oxygen in it, and it has hydroxyl. Okay, and it turns out if you take a mineral like this and you get it hot enough, this hydroxyl OH will come off as water vapor. Okay, so this is a rock that has water in it. To get the water out, you just have to heat it up. Okay, and it turns out that these kinds of minerals are really, really common, particularly in the types of meteorites we think are primordial, the ones that would have been present at the beginning of the solar system to form the Earth. Okay, so there's lots of evidence that the stuff that the Earth originally formed from, these meteorites, may have actually had water in it to begin with. And it's just a matter of getting the water out of the rock to the surface of the Earth. Oh, I should go back and say, this isn't, by the way, the only explanation that's been offered. Of course, we have comets in our solar system. Comets are rich in water, okay, and every so often we would expect a comet to come in and hit us. That's probably going to deliver some water to the Earth as well. So there are various possible ways that we could get water to the Earth, but here's just one example. And I think there's a general consensus this is probably where most of the water came from. Okay, so we have water in the rocks that went to make up the Earth. Okay, and by the way, I have an example of one of those types of rocks, a primitive meteorite, an example of materials that formed very early in the history of our solar system that then accumulated to become planets. This blackish rock here is actually a chunk of the meteorite Allende, which I think was observed about 40 years ago. It's not very old that it was discovered. Okay, and this is a carbonaceous chondrite, which is a particularly primitive type of meteorite, something similar to what we think the Earth was made from. And you're welcome to come up and take a closer look at it after the lecture's over. Okay, so we have this planet, it has water trapped in it, in these minerals like serpentinite, or in salt crystals. How does it get back out? How does it get to the surface of the Earth to form an ocean? Well, this is actually something we observed going on. And in the first pictures I showed you in this lecture, you saw that process occurring today in the form of outgassing, which is, if you have melting happening at some depth in the Earth, which is what happens beneath volcanoes, water in particular, and some other things like sodium, tends to like to go into that melt. So if you melt a rock a little bit deep in the Earth, and there's a little bit of water trapped in that rock, that water is going to tend to run right into the melt. Okay? When that melted rock makes it up to the surface, that water is going to come out in the form of steam. Okay? And what we see here is an example of a piston event, a gas piston event, near Pu'u'o'o, which is the active vent on the volcano of Kilauea. Okay, and what we see here is at the surface of this volcano, the magma is coming up, the molten rock is coming up. Its gas is coming out in the form of steam, and there are other gases present as well, carbon dioxide, sulfur dioxide, and so on. Okay, and the magma foams up, okay, makes all these gas bubbles, these water vapor bubbles that are trying to escape to the surface just like bubbles from a can of soda. Okay, and they're, in this case, actually blowing bubbles in the magma. So the magma is like getting blown up by the gas coming out. It blows up this little bubble of lava until it reaches the surface, and the bubble pops. And then it collapses back down again and blows another bubble. Okay? So what you're seeing here are big gas bubbles blowing up near the summit of Kilauea. And of course, every time one reaches the surface, you see this big cloud of steam come out. Okay? So this is water being delivered to the Earth's surface from the Earth's interior by volcanic degassing. Okay? So once the water is in the Earth, wherever there's a volcano, there's going to tend to be water coming back out again. All right, so are there any questions about that? The origin of the Earth's water and how that water makes it up to the surface? Yes? The question is, what's my favorite theory on where the water comes from? So this isn't really what I do, so I don't know if I'm particularly qualified to have it. But I think there's generally a consensus that most of the water in the Earth is primordial. It came in with the things like the meteorites that originally formed the Earth in the form of hydrated minerals like serpentinite, in the form of perhaps little fluid inclusions, but mostly in those hydrous minerals. And of course, we've had some material added from comets later, but I don't think that people generally believe that that's where most of the water in the oceans comes from. I think mostly it came from the original material that made the planet. Any other questions? Okay. So this story I've just told you of degassing, of water originally being trapped inside the Earth in minerals or fluid inclusions or whatever, and then coming out by a process of volcanism and accumulating in the atmosphere as water vapor and then eventually raining out to form an ocean, that's an example of differentiation. You start out with a lump of stuff that's kind of mixed together. You have rock and you have water trapped in that rock, and they're all in one phase, all kind of mixed together, and then you have a volcano, and the gas gets out the top, and the rocky parts stay behind. Okay, so you've differentiated. You've gone from something that's kind of mixed together, where the water is mixed in with the rock, to something that's been separated out, sorted out. The water's in the atmosphere, and the rock stays in the ground. Okay, and in fact, we live on a differentiated planet. Okay, not just in the sense that a lot of water is accumulated at the surface, but also in the sense that deep within the planet, things have sorted themselves out into layers, in particular layers according to density. Okay, so in our planet, there are, crudely speaking, 3 major layers. Okay, oops. Huh, that's kind of weird. Okay, so we have the crust, which is what we sit on today, and it's so thin that it actually wouldn't show up very well in this picture. It's about 0.5% of the radius of the Earth, something like that on average. Okay, so it's about 1 pixel wide here, but it wouldn't be big enough for me to label, but there is a crust on the outside. There's a mantle, which actually makes up the bulk of the mass of the planet, okay, and is a little bit less than the outer half in terms of radius. And then we have a metallic core, which is mostly iron metal with some nickel mixed in, and then a few % of other elements that we don't really know what they are. We don't have a sample of the core. We can't just do a chemical analysis of it. We have to infer its properties from a distance. Okay, and these are sorted according to density. Okay, crust is less dense than mantle. Mantle is less dense than the core. And the oceans are less dense than all of them, so they sit on top of the crust. Okay, and then of course we have an atmosphere, which is the least dense of all, so that sits on top of everything. Okay, so the Earth is a differentiated planet, and it's separated into layers. Metallic core, densest at the center. Rocky mantle, next most dense. Crust, the least dense rocky part. Oceans, less dense than the rocks. Atmosphere, less dense than the oceans or the rocks. Okay? And in fact, we have samples of these things here. We don't have a sample of the Earth's core. Okay? We haven't been able to drill that deep or even close to that deep, movies notwithstanding. However, because we have other bodies in our solar system, we have a few planets probably that were able to form and differentiate and make their own metallic cores, and then they kind of met an untimely end. They got destroyed. They got pummeled into little pieces, and occasionally those little pieces fall on the planet in the form of differentiated meteorites, probably the most famous of which are the iron meteorites. This is a sample of an iron meteorite. It didn't naturally come in this square shape. It's been cut with a saw and polished, so it was originally a lump. Okay? And you're welcome to come up and look at this. It actually, you can see the little metal crystals in it. The Earth's outer core is actually probably molten, but this core, when the body got broken up, it froze. Okay, and probably before the body ever got broken up. So that's an example of a metallic core. This is an example of what rocks look like in the mantle, and the color sort of matches. That was kind of the intent anyway. And this is kind of a greenish rock. And it's green because its characteristic is that it's got a lot of them. It's in large part made up of a mineral called olivine. Olivine, it's green. The name hopefully is a little bit self-explanatory, kind of an olive green color. That contains magnesium and silicon. It's pretty dense, something like 3.2, 3.3 times as dense as water. Okay. And then we have the rocks that are typical of the crust. And in fact, on the Earth, we have two types of crust that we'll talk about in more detail in future lectures. This is a rock called basalt, kind of darkish colored, gray or black. This is the characteristic rock of the oceanic crust. Here we have a light colored rock. Okay. And this is this is a granite, by the way. This is characteristic of the continental crust. Okay. And it turns out you have a special ability that you didn't realize you had, which is that you can actually come up after class, if you'd like, and see if you can tell which is the most dense. Turns out that human beings are pretty good at evaluating density. If you can put something in your hands, you can make a pretty good guess of its relative density. I don't know why we can do this. Maybe it has to do with, like, you know, when we were roaming around in the savannas, we had to pick the right fruit that was nice and heavy and not rotten. Who knows? But it turns out that if you practice a little bit, you can actually detect differences in density for rocks like this, 5% or so. You're really good at it, even if you don't realize it. So I would encourage you to come up and see. Can you figure out for yourself that the metal is a little bit more, actually a lot more dense than this greenish rock, and that the greenish rock representing the Earth's mantle is more dense than either of these other two rocks? And can you even tell that this darkish rock is a little bit more dense than this lightish colored rock? Yes?
So the density for rocks has more to do than just weight?
Density is defined as the mass per unit volume, right? And it turns out that the density of a rock, to first order, you can think of as being determined by its chemical composition. Okay, so metals are very dense. They're like 8, 9 times as dense as water. Minerals that have lots of magnesium in them, like this olivine, which is really rich in magnesium, are pretty dense. Rocks that have lots of silicon and aluminum in them, like these light-colored rocks, tend to be less dense. And so you can essentially order rocks according to their chemical composition. If it's got metal, it's really dense. If it's got lots of magnesium, it's probably pretty dense. If it doesn't have very much magnesium, it's probably less dense. Any more questions? Okay. Let's see, we're about out of time, actually. Why don't I just do a little bit more? I'm not going to quite get through everything today, but that's okay. Okay, so that's the chemical layering of the Earth. These light-colored rocks, characteristic of the continental crust. These dark-colored rocks, characteristic of the ocean crust. At the surface, they're the least dense rocks we have in large quantity on the Earth. And they're 2.8 times as dense as water, maybe 3 times as dense as water. Then beneath them we have the mantle, rocks that are maybe 3.2, 3.3 times as dense as water. And then in the middle we have metal, which is under the pressures of all the rock on top of it, something like 10 times as dense as water. Big difference in density. So least dense at the surface, most dense at depth. In addition, we actually have physical layering in the Earth, okay, which corresponds both to differences in composition, going from crust to mantle to core, and also to the fact that the center of the Earth is very hot. Okay? The Earth has radioactive elements in it. Those radioactive elements are decaying. That creates heat. That heat has to get out and radiate away to space ultimately. And so the way that heat gets out is by getting really hot in the center and conducting or convecting that heat out to the surface. If you dig down from the surface, you're going the other way. So things are getting progressively hotter the deeper you get. In general, rocks aren't really very different from like butter or ice cream. The warmer they get, the weaker they get. Okay, and of course, eventually they're going to melt. But even when they're still solid, a rock that's hot is generally going to be weaker, less able to withstand shearing stresses or any other kind of stress than a cold rock. Okay? And so what we observe at near the Earth's surface in particular is that we have two layers differentiated from each other by their strength. The top 100 kilometers or so of the Earth is what we call lithosphere, lithos being like rock. Okay? And that part of the Earth is essentially rigid. Okay? It doesn't flow very easily. It's like what you would expect a rock to do. Okay? It can break, it can fracture, but it won't flow. Once you get below about 100 kilometers or so, things start to get so hot, even for rocks, that they become kind of weak. They start flowing. Even though they're still solid, they can still flow if there's something pushing them around. And we're talking about flow, by the way, on long time scales, millions of years, not just pulling it with your hands. Okay, so I'm going to come back and do this again on Wednesday, but just to give you a little bit of a preview, in addition to the Earth being differentiated by chemical composition, it's going to turn out to be really important that the Earth is differentiated by physical strength. All right, so please be sure to go to your labs this week. Try to clear up any registration issues you have. And if you haven't yet already, go to the website. You can get all the lecture notes there. And please feel free to come up and take a closer look at the meteorites and crust and mantle samples.